Hello, dear students of third year secondary. Uh, this is your physics session. My name is Ahmed and I teach physics. Today, would like to continue talking about chapter 7 and the laser. We'd like today to talk about the laser applications. From the applications of laser, many things like holography application also is used in many fields such as medicine, communication, military, industry, computers, surveying, arts, and space research. So laser as a theory has many applications. We don't take laser just to know the theory, but also to understand that it has many applications in life and in many other fields. We will take the first application, which is holography. Holography is simply a kind of forming images, but in 3 dimensions. How holography is done is simply by using coherent rays, light rays, and coherent light rays could not be achieved without laser. So if you look at the diagram, this one now, here you have rays coming from the laser, and the rays coming from the laser, they help to form a 3-dimensional image. And today, inshallah, we will talk about how this 3-dimensional image is formed. Before we go deep inside the holography, we'd like to introduce first the image formation. Any image, like in any used like camera, and we take an image using a simple camera or digital camera. It depends on many things, such as like the light falling on the object and the reflection of the light received by a sensitive photographic plate or film, and then developed to get the image. So in general, the image are formed by recording reflecting rays forming from an object. So the object, you have light falls on an object, and then this light will be reflected out from the object, received by sensitive film or sensitive photographic plate, and then the photographic plate will record the image in the form of points. Each one of them represents different intensity of light. So the reflected rays carry information from the object, and these information are 2 kinds of information. Now we talk about now any reflected rays, they carry information from the object they reflect from. These information are the difference in optical densities and the phase difference. Now we have 2 things here coming from the reflected rays. If we care about the difference in optical densities only, we can form a normal image, whether black and white or colored. But if we would like to have the whole truth or the whole information coming from the object, we need to add another feature to this, which is not only the optical densities, but also the phase difference. And what we mean by the phase difference is the phase difference of the reflected rays will tell me about the surface of the object, which means the topography. If you have some of the objects higher than the other, or if it is flat, completely flat, or it has some grooves or some internal parts. What we mean by this is by recording the whole truth, which is 2 things coming from the reflected rays, the difference in optical densities, and also the phase difference, we can have all the information coming from the object, and we can have the three-dimensional image. But in normal cases, in normal images, we don't have um, the whole truth coming from the object, but only we have a two-dimensional image, which can be formed if only we care about the difference in optical densities, not the phase difference. Okay, so what makes the difference is the phase difference. What is the phase difference? The phase difference is simply an indication of the topography or the surface of the object itself. It gives me the three dimensions. So the phase difference equals the path difference, which results from different height of the surface of object, multiplied by 2 pi divided by lambda, where lambda is the wavelength of the rays. So here you have lambda, the wavelength, pi, we know it's constant. So we need now to understand what is the path difference. What is the path difference? Rays do not have the same path. Why is this? Because there is a little bit of difference like between each ray, depending on the topography or the surface or the curvature of the object itself, as they are reflected from different heights of surfaces. Okay, so the topography of the object affects the path difference of the reflected rays. And that's why if I have the phase difference plus the intensity of light, we can have the whole truth coming from the reflected rays. How normal images are formed? We need to make a comparison between the two dimensions formed by normal image taken by camera and the three-dimensional image which can be seen using a hologram. Now, let's now talk about the normal image. The photographic plate records the variation in the intensity of reflected rays. This is how the image, the normal image, is formed. You have an object, and then you have light falling on the object. The light rays will be reflected out from the object, and it will fall on a sensitive plate. And then by developing this sensitive plate, we can have an image. So the image of the body is formed by collecting the information obtained from the reflected rays from the body. The reflected rays are different in their optical density. Now, what we mean by optical density is how the light differs in its intensity or how illumination varies between rays coming out from the object. And because the intensity of light, I, is directly proportional to the square of the amplitude of the wave, so by increasing the amplitudes, I have different densities. And that's why optical density is directly proportional to the square of the amplitude of the wave. Okay, using a laser to form holography depends on very important mechanism, which is you have the rays coming out from the laser. Now, if I split the laser beam into two parallel groups, okay, of course, laser has coherent waves. Now, I split the beam coming out from the laser into two groups. Reference beam and another beam which will fall on the object. What is a reference beam? They are parallel rays, have the same wavelength of the reflected rays from the body, and we use this to form a hologram. How to form a hologram? If you look here, this is an object, which is like a toy, like a lizard. And here you have so if you look at the diagram here, this is a toy of a lizard or dinosaur toy. And this is the laser. The laser here, all these rays coming from the laser, okay? Now, as you see here, group of beam from here to here, okay? This group, they hit the mirror and they are reflected on a photo plate or photographic sensitive plate. And you have also other rays hitting the object and then reflect to the photo plate. So object wave and reference wave. Now, these waves, they all have the same wavelength, they are coherent, and because they come to the photographic plate, the reference beam and the reflected rays, both of them, they reach the photographic or the photo plates, and they interfere with each other. So let me talk again about the mechanism of forming a hologram. This is how hologram is formed. You have the laser beam, coherent waves. They split into two beams. One beam is called the reference beam, does not hit the object, but it hits the mirror and then reflected to the photographic plate. And the other beam coming also from the laser, having the same wavelength, hits the object and then reflected to the photographic plate. The interference between this group, the reference and the reflected rays, the reference beam and the reflected rays, they will interfere with each other and they will form fringes here. As you studied last year, the interference of light can form fringes, and these fringes can indicate the image. So here, the photographic plates will record the fringes of the interference between the two beams, the rays coming from the object, the reflected rays, and the reference beam. This is how hologram is formed. So let's now put them in steps. The laser beam is split into two beams, okay? One is the reference beam, and the other is used to illuminate the body. So now we are talking about how we start forming a hologram. We use a laser, okay? Because the laser is the only kind of source of light that will provide me with coherent waves. Now, the laser beam will split into two beams. I use the first one as a reference beam, all right? And the second one, I will use it to illuminate the body. Step number two, the two rays meet at the photographic plate. The two rays, what we mean by the two rays, the two beams of rays, the reference beam and the reflected rays. They meet at the photographic plate and they interfere, as we talked earlier, they interfere with each other, forming fringes. And these fringes decode for the image in 3 dimensions. So the fringes will be recorded as 3-dimensional image. Now, I got now the photographic plates. After developing the photographic plates, I develop it, the image appear coded, all right? So the image cannot be seen by itself now, it's not ready to be seen. But in order for me to see the image after it is coded on the photographic plate, I need to illuminate it using laser of the same wavelength. that I used earlier to form the image in the first place. So I will use the laser that will provide the same wavelength of rays to shine or to illuminate the image on the photographic plate. Now the image is coded, it is not clear image like the image that we see on normal photographic plate. It is coded, which means it is not ready to be seen. But once I illuminate it, when I shine light on it, the coded image will have three-dimension image is seen as a hologram. Now, we see this by the naked eyes. We don't use any extra device to see the three-dimensional image. So the hologram is an image in 3 dimensions that I can see by shining a laser beam with the same wavelength that I used to form the hologram in the first place. When the laser beam shines or is directed toward the photographic plate, I can see the hologram. What's strange about the hologram is I don't see the hologram as a real image, but I see it virtually. Virtually means I look at the photographic plate once I shine laser on it, and I see the image virtual. Virtual means I see it into the hologram. They are not real, cannot be obtained on a screen, but I see it as if I look at the mirror or as if I look at something which is not a screen. But I see it in 3 dimensions, which indicates the whole truth about the image. I can see the image in 3 dimensions. I can see if it is has some parts up and down or grooves or internal parts. I can see many features that I cannot see in 2 dimensions image formed by normal camera. So the hologram is defined as a coded image formed by the interference of the reflected beam with the reference beam to form fringes. So this will form fringes. And after developing the photographic plate, I see it. So what's a hologram? A hologram is a coded image formed by the interference of the reflected beam with the reference beam to form fringes. So as we said earlier, a hologram is formed simply not like a normal image, but as a result of interference between 2 beams of light. One of them coming from the object, reflected rays, and the other one is called the reference beam. And they interfere with each other, and the result of their interference is fringes, and these fringes will code the image on the photographic plate. Once the photographic plate is coded with this image, I can now shine laser on it, on this coded image, to see it. Okay, so by knowing the hologram, and we'd like now to compare between the holographic image dimensions, the normal one. Here is the point of comparison in the photographic image and the hologram in 3 dimensions. The first point of comparison is the information recorded. The photographic image, the normal image formed by any camera, records half the truth. What we mean by half the truth, it records only one information coming from the reflected rays, which is the variation in optical densities. The reflected rays carry information from the object. These information are the difference in optical densities only. As you see here, the difference between these reflected rays coming from the difference in optical densities only, which indicates the features in 2 dimensions. But if we compare this with the hologram in 3 dimensions, we have the reflected rays coming, and they interfere with the reference beam. So in hologram, we have 3-dimension image. The whole truth is recorded by a hologram. What we mean by the whole truth is the reflected rays, they carry information from the objects, and these information are complete information, whole truth. they carry not only the difference in optical densities like normal image, but also the phase difference between these reflected rays. Now, the phase difference will give me the topography of the surface of the object, which means that I can see the object in 3 dimensions as if it is real. So this is the difference number 1. The point of comparison next between the photographic image and the hologram is the light beam used. Now, in photographic image, I use normal light beam. It can be provided by a flash or by normal light. It doesn't have to be coherent. But in hologram, I have to use laser. Why in hologram I have to use laser? It's because laser provides coherent waves. And this is the only source that I can depend on to achieve the coherent or to like secure the coherence that I want. And coherence cannot be achieved by normal flash of light, but I need laser. The second point of comparison between, or the third one, comparison between photographic image and hologram, the mechanism of construction, which means that how the image is formed, how can I obtain it? The photographic image can be obtained by normal camera, as we know. How light beam incident directly on the object. So very simple and direct. I have light, the light beam falls on the object and reflected. Simple. But on hologram, it is not this simple. In hologram, I have a laser beam split into 2. One is reference and the other one is incident beam. So in normal photographic, I have one beam of light incident. But in hologram, I have the beam coming from the laser split into 2. One is used to illuminate the object, and then I will receive it as it reflects. And the other one is the beam that we call the reference beam. Next, we have seeing the image. How we see the image after knowing how the image is constructed using the normal photographic image and the hologram. We need to understand now how to see the image after it is formed. Now, in photographic image, the only thing I need to do is just develop the photographic plate and see it ready. Once photographic plate is developed, I develop the photographic plate and then it is ready. I can see it at any time. But in hologram, things are different. I need to reconstruct by using laser to illuminate the image, which means that I don't have a ready image. I need to reconstruct it using a laser, as we talked before. So I use a laser, I illuminate the image using this laser, and this is how I see a virtual 3-dimensional image as a hologram. Okay. The next point of comparison is characteristics of the image. By a normal photographic plate or normal image that can be obtained using camera is a real image. What do we mean by real image? I can obtain it or I can get it on a photographic plate or I can get it ready. I can see it at any time and it's 2 dimensions. In hologram, it is coded. It's not like a real image that I can see directly. It is coded and it's coded as interference fringes. And once I shine the laser, I see it as a virtual image. Like when you look at the mirror, you see inside the mirror. So the object cannot be obtained on a screen, but actually it is inside the image. The next point of comparison is the number of images used. The number of images that can be formed in normal photographic plates, once I have a normal camera, is 1 image in 1 photographic plate. So I can have 1 image in 1 photographic plate if I use a normal camera. Now, By using a hologram, I can have many images can be stored like tens in one hologram. So I can have one hologram that contains 10 images, okay, more than one. So it is very convenient. Now, in normal photographic image, I have stationary image. What I mean by stationary image is image that they don't move. These images, they don't move. Once recorded, once the photographic plate is developed, I see the images. They don't move. But the advantage of having a hologram is these images can also move. And as we see in some movies and some, like if you go to three-dimensional cinema or theater, you can see that things can be three-dimensional, and this can be done using a very advanced hologram using in this kind of theaters. Now we finished talking about the hologram and then comparison between the normal images and the holograms. Let's now talk about other applications of lasers. We know that lasers, they are like, we have applications everywhere in many fields of life, not only holograms, but we have other things such as in medicine. For example, in medicine, I can use laser with optical fibers to make something called endoscopy or endoscope. Now, endoscope is using optical fiber, and these optical fibers, they use laser beam, and this laser beam can act to illuminate something inside the body, or it can form images, or it can form even holograms in 3 dimensions. So I use endoscopy for diagnosis to know the disease, and for ophthalmology. Ophthalmology is the science of studying everything about the eye and the sight. And I can also use the laser in operative surgery to correct uh, short and long sightedness. The people, they suffer from myopia or hypermyopia or anything not correct in the way they see things. If they can see things only if they are close, or they see things if they are very far away, and so on. And also the laser can also used in treat or treat something, it was a disaster before. It is retinal detachment. Retinal detachment can cause blindness if a person has his retina, which is the part sensitive to light in the eye. Detached means separated from the optical nerve, which means that the optical nerve cannot receive information from the retina, and as a result, the person will suffer from blindness. Before, it was hard operation, but now using laser, they can use the laser to uh, like not to reconstruct, but to attach the retina back to its normal place. So to bring the retina back to its normal place, so that the person will see again using a very simple laser. Um, Now, these are some of the applications in the field of medicine. In communication, using laser in optical fibers instead of telephone cables. Now, telephone cables, they use electricity, and as we know that electricity, when transferred over long distances, they use some of the energy. But if I use laser and optical fiber, I can guarantee that telephone cables will carry more than it carries by using the normal technique of electricity. And this is very useful to save energy and also to guarantee very high technology in communication. In military, it's like laser is everywhere, applied in rocket guidance missiles. And these missiles, they can be guided using laser, so the target will be 100% sure that the missile will hit the target without missing, because it's guided by laser. Also, the laser radar, which is using the laser to detect the position of enemy aircraft or enemy position, and we call it LADAR, LADAR, which stands for laser radar, short for laser radar, LADAR. And this is used to point the exact location and coordinates of a certain targets, military targets, even from very high place using satellite, for example. And another application in military is smart bombs. Smart bombs, they have a certain technique. They can hit a target and they can leave some target and they hit the other. So that's why they call it smart bombs. They choose the target very well, and how they operate. They operate using a device. It depends on laser to hit a specific target and not the others. Laser also in military can be used in Star War to destroy missiles and plane after they are launched. For example, if an enemy launch an aircraft or missiles to hit another target and you would like to destroy this, you can destroy it immediately after it is launched, and you don't have to wait until it hits you. So this can be done using also laser guidance technique. We call this technique the Star War. In industry, laser also has many applications in engineering because laser, as the beam of laser, can provide heat. So they can generate heat, and this heat can be very, very immense and very high that can reach even melting metals, such as even iron. So, and the good thing about laser is the heat is not spread over long distances. It is only in the position needed, exactly in the point that you want. So for example, you can have a metal and you want this metal to melt at specific points. So the heat will be very high at specific points, not everywhere in the metal. And this provides very accurate melting technique for metals. Also making holes in diamonds. We know that diamonds, they have very high hardness, and they are very hard to scratch and very hard to break. But we can use laser to make holes in diamond, and which is used in jewelry and other things. Computers, we are familiar with laser recording or CD. CD also use laser to record information. And laser printer is, as we all know, that it provides colors, very accurate colors, and it's like better than the normal printing that depend on ink. So laser printer is much better than the ink one. So these are applications of lasers in many fields. And by this, we finished the parts talking about laser, which is chapter 7. Let's now talk about chapter 8. Chapter 8 is really interesting one. It's an introduction to electronics. And it is a chapter that talks about how humans transferred from normal science age into the science, the age of technology and high tech, and using very accurate devices. So we need to first to start talking about electronics is start from scratch. We know that concerning electricity, we have some materials, they conduct electric current, and other materials, they don't conduct electric currents. And we know that electric conductors, they allow electric current to pass through, or electric charges, they are allowed to pass through. Insulators, on the other hand, they don't allow electric currents or electric charges to pass through them. Now, so we have conductors and we have insulators. Now, in between, we have some materials that they are not conductors and they are not insulators. They have characteristics of both of them. They don't conduct and they don't insulate. So in this case, we call them semiconductors. Now, semiconductors, they are different from conductors. In what way? Let's compare between them in simple like table like this, and let's see how they differ from each other. Conductors, they are conductors and semiconductors, they are made of atoms, of course. But conductors, they are formed inside a structure called crystals. And inside the crystals, you have positive ions and free electrons attached to them. This is how the crystal is formed regarding any conductor. So it's like positive ions, and then you have a sea of free electrons moving freely around them. This is the structure of the crystal of any conductor. In semiconductors, atoms are joined by covalent bonds. Thus, different structure. You have atoms, and these atoms are joined by covalent bonds. So, complete different structure. Conductors, positive ions, and free electrons swimming around. But semiconductors, you have atoms joined by covalent bonds. Different structure. And this different structure will have different properties. Now, the charge carriers, what we mean by charge carriers, if conductors, they are allowed to conduct between two different places, like the electric current will have to go through them, you have you have a charge carrier, which carries the charge, electric charge, and this charge is carried by N. What we mean by N here, negatively charged particles. Negatively charged particles, we mean by this electrons. So N stands for negatively charged particles. They carry the charges. But in semiconductors, we have negatively charged particles, the electrons, and also we have positively charged particles. So in this case, we have two types of charge carriers in semiconductors. But in conductors, we have only one type of charge carriers, which are the negatively charged carriers, electrons. Now, another point of comparison between conductors and semiconductors, the effect of temperature on the number of charge carriers. Now, what we mean by this, if we subject a material like copper, say a conductor, subject this conductor wire made of copper to temperature, like increase its temperature. What will happen? The charge carrier, which electrons in this case, constant, they don't change, despite that I raise the temperature, but not too much. Okay? I raise the temperature in average way, so the charge carrier, they are still the same. The number of electrons, free electrons, still the same. Maybe they increase in their mobility and they move a little bit faster with high kinetic energy, but the number of them don't change. The numbers, they don't change. Now, how about semiconductors? The N directly proportional to T. What we mean by this is the negatively charged particles, electrons, they increase with the increase in temperature. What we mean by this is by raising the temperature, more electrons will be there, or more negatively charged charges will be obtained or created or originated. The same for positively charged particles will also increase with temperature. So in a summary, the charge carriers, they are the same in conductors, whether I raise the temperature or not. But in semiconductors, if I raise the temperature, the charge carriers number increases. The number increases by raising temperature. How about the effect of heat on electric resistance? We know that electric resistance, we took it in chapter 1 when we studied Ohm's law. We know that the resistance depends on temperature. If the temperature increases, the resistance also increases, and we know that from chapter 1 that's because you have random moving of electrons, and this random moving of electrons will collide with each other, and this will prevent a smooth movement of electrons, which means that the resistance will be higher. So if the temperature increases, the resistance increases. So in this case, we have to look at the semiconductors. If the temperature increases, the resistance increases, which means that the current will be more. Okay, so the current will be less if I raise the temperature. For conductor, like you have a wire made of copper, you raise the temperature, what do you expect will happen to the current? The current will be less. because the resistance will be bigger. And we know that the resistance and current, they are inversely proportional from Ohm's law, first chapter. So here, if I have a conductor and made of copper, for example, a wire made of copper, and I raise the temperature, what happened to the electric current? Increases or decreases? The electric current decreases in conductor because the resistance increases by temperature. Okay, how about semiconductors? In semiconductors, the exact opposite happens. By raising the temperature, the resistance falls down, which means that the current will increase. And we will understand from the following diagram how this happens. So in semiconductors, by raising the temperature, I have the current intensity higher because the resistance will fall down. This is the comparison between semiconductors and the conductors. Let's now focus on the semiconductors. What is the semiconductor? We said that conductors, they conduct electricity, and insulators, they don't conduct electricity, and we have materials in between. We call them semiconductors. And these semiconductors, they have characteristics between conductors and insulators. So the definition of semiconductors, they are materials, their electric conductivity is between conductors and insulators. Their conductivity increases by the increase in temperature or by adding impurities. We call adding impurities doping. So what is semiconductors? It is a material which has characteristics or properties between insulators and conductors. Okay? And the second thing I need to say about semiconductors, how to increase their conductivity, because they are between this and this, but how to increase their conductivity? There is two ways to increase the conductivity of a semiconductors. First one, increasing temperature. The second one is by adding impurities. And we will explain each one of them in details later. So this is the definition of semiconductors. Examples. On the periodic table, we have metals and we have non-metals. The metals on the left-hand side of the periodic table, and the non-metals on the right-hand side. And in between, you have metalloids or things in between. So metalloids or things in between, such as silicon and germanium. The silicon and germanium, they are between metals and non-metals. So we call them semiconductor. They are made of crystals because they are solid state. So what is a crystal in general? Crystal is a regular geometric arrangement of atoms in the solid state. So the crystal is how atoms are arranged. And what's amazing about crystals, that if you look at a crystal under microscope, you see it is as if it is designed by an engineer. It is beautifully made by repeating units, and they are arranged in a geometric way. The geometry is perfect geometry, and it's as if it is designed by an engineer. So if you look here at this diagram, when you look at the crystal of silicon, here is the atoms of silicon, this one. So you have silicon atoms here. And as you see here, it looks perfectly in a crystal. It looks as if designed exactly using geometry. So in 3 dimensions, if you look at another kind of crystal, look here, you have an atom, and you have atom here, and you have here the structure is repeated in units. What we mean by this is 1 unit of a crystal. If I have this repeated beside it, above it, under it, to the left of it, this will give me the whole crystal. But this is called the units because by repeating the units, I can have the whole crystal of any material in solid state. This is the general idea of a crystal. But let's now focus. We have, before discussing further the semiconductors, we need to of electrons. We know that electrons, they are negatively charged particles and they revolve around the nucleus. We need to know what are the types. Are all electrons the same? Are all of them the same, or they are different? Actually, they are the same in charge, spin, and general characteristics as subatomic particles. But we need to investigate that they are different according to the energy and the behavior they conduct. So we have innermost electrons. These electrons are bound to the nucleus. They are close to the nucleus, attracted by the positive charge of the nucleus, and they don't easily move without huge amount of energy. We call them innermost electrons. They are attached and closely to the nucleus. We have another kind of electrons called the valence electrons or the valency electrons. They move freely within the inner atomic distance. So they have free movements, but they don't go too far. They are just moving freely within the interatomic distances. What we mean by interatomic distances? The distance between atoms. Okay, the small little distance between atoms, they move freely between them. The third type of electrons, we call it free electrons. The free electrons, they are not valence electrons. They are moving freely within the whole crystal. They are not bound by the distance between atoms, but they think that the whole crystal is their home, so they move everywhere they can within the crystal. We call them free electrons. So these are the three types of electrons, and we need to understand the difference between them so that when we talk about the semiconductor, how they conduct and how they behave, we understand what we mean by each terminology. Now let's start by talking about pure silicon crystal. We know that a silicon is a semiconductor. If it is pure, this is how it looks. So this is how it looks. The silicon crystal, how it looks. As you see here, this is Si, silicon, Si, silicon, Si, Si, all these atoms of silicon. And we know that silicon is tetravalent. Tetravalent means it has 4 electrons in the outermost shell. So consider this silicon, 1, 2, 3, 4. And you have also from here 1, 2, 3, 4. So which means that every atom of silicon has 4 electrons to contribute to the crystal. And by this I have pure crystal of silicon. Okay, this is how silicon. So every atom has 4 electrons, and these 4 electrons, they join with the atoms of silicon from everywhere by covalent bond. And the covalent bond is provided by sharing electrons. So here, this covalent bond between this Si and this Si is provided by 2 electrons. Now let's semiconductors. The pure semiconductors like silicon crystal is tetravalent atom like silicon or germanium, as we said. And what's important about the pure silicon or the pure semiconductor is the concentration of free electrons, which is the negatively charged carriers, equals the concentration of the holes or the positively charged carriers at any temperature. Now, this is the definition of pure semiconductors. Pure semiconductors, I have the carriers of negative charge equal carriers of positive charge at any temperature, which means this is now pure silicon. Okay, pure silicon, concentration of this equal concentration of this. The negatively charged carriers equal the positively charged carriers, and this is now pure silicon. Now, I'm not going to benefit from it if it is pure. To increase its conductivity. One way to increase the conductivity of semiconductors is by raising temperature. So how raising temperature will increase the conductivity of semiconductors. شوي شوي. How raising temperature increases conductivity? Now, we know that for electrons to move from their place, they need energy. So this is the pure crystal of silicon. Okay, this is the pure crystal of silicon. And if the temperature increases, one electron, say this one or this one, okay, will acquire enough energy to break free from the covalent bond. Now, leaving its place, when the electron leaves its place from the covalent bond, we call this a hole. A hole means a missing position of an electron. So if an electron misses its position and leaves, we call this a hole, which is considered a positively charged carrier. So a hole is considered a positively charged carrier because it's a missing electron. And this can be done by raising temperature. So again, if I have a pure silicon crystal, you raise the temperature, you have one electron in the covalent bond will acquire the energy, will break free, and then the place which was occupied by this electron is now a hole. And we consider this hole now a positively charged carrier. Okay, now here is the mechanism. If an electron absorbs enough energy from raising temperature and breaks free, leaving a vacancy or a hole, which is soon filled with another electron, and so on. Now, this can be explained as this hole is a place which was occupied by an electron. Now, it is missing an electron, so it might snatch an electron from here. So suppose an electron from here breaks free from the covalent bond and comes to occupy this hole, leaving this place empty. And this place will have a hole, and this hole will maybe attract another electron to jump and replace it, and so on. So what's happening is this hole is going to jump from one place to another across the crystal. And this can happen until we reach something called thermal or dynamic equilibrium. Now, this kind of movement of holes or movement of charge carriers can continue until we reach a thermal or dynamic equilibrium. What is the dynamic equilibrium or the thermal equilibrium reached? It is reached when number of broken bonds per second are equal the number of mended bonds per second at a certain temperature. What's the meaning of mended bonds? Mended means recovered. If I have a bond broken by the electron, one electron is missing, it will be mended. Mended means repaired or corrected by another electron. As we said, when you have a missing electron, it will form a hole, and this hole will snatch another electron from a nearby bond, and so on. So by snatching another electron, the bond will be mended or corrected or repaired, and this can happen at a certain temperature. Now, if the number of broken bonds equal per second, which is the rate of broken bonds equal the rate of mended or repaired bonds, at a certain temperature, this is called thermal equilibrium. Okay, so at any temperature, the number of free electrons and holes remains constant at every temperature. Increasing conductivity can be done, as we said, by increasing temperature, but there is another way of doing that, which is increasing the uh, the, the conductivity by using impurities. The crystal, if it is pure, it does not conduct electricity readily, and it needs some encouragement. And one of these encouragements can be the temperature, if we raise the temperature. Another form of enhancement, or how to push the crystal to conduct electricity more, is by doping. Doping means adding impurities. What we mean by impurities, we add another atom different in its valency from the original atom inside the crystal. So adding impurity means adding an atom, and this atom has to be different in its valency. Maybe it has one less electron or one more electron in its outermost shell, and this little difference will cause the conductivity to increase. And because of this, we divide doping semiconductors into two types. And because of this, we have N-type semiconductors and we have P-type semiconductors. Let's start by the first one, the N-type semiconductors. They are defined by the concentration of free electrons bigger than the concentration of holes in the negatively charged carriers, bigger than P, the positively charged carriers. When this is the case, I call it N-type. Why N-type? Because number of N bigger than number of P. So I call it I call it N-type semiconductors. And this can be done, how can be done? How can I increase the number of negatively charged particles, the electrons? We know that silicon is tetravalent, has 4 electrons in their outermost shell. If I add another atom, which is pentavalent, pentavalent means it has 1 extra electron, and atoms that they are pentavalent, such as phosphorus, P, or antimony, Sp. And if you look here at what will happen if I have N-doped silicon, this is the atom of silicon, which is indicated by this dark color, the gray one. And the doping or the strange atom is the red one. And pentavalent, it's group V atom, group 5 atom, which is pentavalent. So this is now pentavalent. So I inserted an impurity atom, which is from group 5 pentavalent, into this crystal. This will have how many electrons around? Every silicon has 4. 1, 2, 3, 4. 4 electrons around this. But this one has an extra electron. Wow. This extra electron will make the difference. Because now this extra electron will make the concentration of the N bigger than the concentration of P. They are no longer neutral. Okay, so what happened if I now would like to consider the crystal having an exact atoms? So this is silicon, silicon, silicon. You have here negative, 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 negative. This is the electrons around, 4 electrons around each silicon. Here is Sb, the antimony atom, has how many electrons in the outermost shell? 1, 2, 3, 4, 5. Wow. So this extra electron is the 5th valence electron of antimony atom. Okay? And this extra electron will make the number of negative more than the number of positive. All right? Now, let's now consider that this is pentavalent atom doping. It's doping means adding a strange atom of antimony, Sb, to the crystal of silicon. And that's why, because it has extra negatively charged particle, we call this crystal or this semiconductor, we call it N-type. N-type means the N is more than P. The other type of semiconductor is the p-type semiconductors. The p-type, the opposite, the concentration of free electrons in is less than the concentration of the holes. Now, how to achieve this? How to make the number of electrons less than the number of holes? I can do the opposite. Now, I can get the impurity from an atom which has one less electron than silicon, which means trivalent, because silicon is tetravalent. Now, look here. This is p doped silicon. P doped silicon. How it's done? Look at here one. These atoms here, they are silicon. All this silicon. The atom here in the middle, it is not silicon. It is from group 3 atom. Group 3 means the trivalent. And because it's trivalent, each one has 3 electrons. 1, 2, 3. How about this fourth covalent bond that it needs to share with this silicon atom? It can't. So because it does not have the electron to make this bond with this silicon, I call this place an empty place that should be filled with an electron. So I call it a hole and I put plus. Plus indicates missing position of electron. So by putting an atom from group 3 that has trivalence, it has 3 electrons only around, it shares with 3 silicon atoms, but the fourth silicon atom cannot form the covalent bond with because it's missing 1 electron. In this case, the missing place of this electron is considered a hole. So this can be explained if I have silicon and boron. Boron is trivalent. It's an element, trivalent. It has 3 electrons in the outermost shell. So here you have electron from this silicon, this electron from this silicon. Okay. Here boron shares with this silicon electron, share with this silicon electron, share here with electron. So how many? 1 electron from boron, 2 electrons from boron, 3 electrons from boron, and the fourth place does not have the electron necessary to form the covalent bond with this silicon. So in this case, this is considered a hole. So this hole provides the p-type of conductor. So the trivalent atom doping, such as boron, the symbol of boron is B, will give me a p-type semiconductor. This is how the p-type is formed. Okay. Now, to summarize the difference between N and P, here is N, you have extra electron. By having an impurity with group 5, which means that pentavalent. On the other hand, if you have p-doped silicon, you get the atom of the impurity from group 3, for example, that has 1 electron less than silicon. So that's why the place missing of electrons is called a hole. This is the comparison between N-type and P-type of semiconductors. And our last diagram indicates that this is the antimony and this is silicon. How many electrons are around silicon? 1, 2, 3, 4. And this, the antimony will share with the silicon here, and it has impure, will donor impurity contributes free electrons, which means that antimony will have extra electron, and this extra electron will be donated to the crystal. All right, boron will the opposite. Boron lacks 1 electron, short than silicon, and that's why it provides the p-type, because it accepts it. It's called acceptor impurity because it creates a hole. And this is how things are done. We leave. It's give reason by doping semiconductor crystals will remain electrically neutral. So which means that I add impurities, but still the crystal electrically neutral. Why? How can I provide the crystal with impurity and I still have neutral, electrically neutral crystal? It is simply because the overall number of positively charges equal the overall number of negatively charges. The concentration of this equal the concentration of that. That's why the overall charge on the crystal is neutral or zero. Negative charges equal the number of positive charges, and by this we come to the end of our lesson. We are now, inshallah, next time we continue to talk about the law of mass action in semiconductors, and by this we come to the end of our lesson for today. Today we discussed the applications of lasers, we discussed also the holograms, and we discussed semiconductors, the N-type and P-type, and how we increase the conductivity of semiconductors. Next time we continue talking about the law of mass action of semiconductors, and by this we come to the end of our lesson. Thank you so much for listening. Don't forget to drop or leave any question that you have. I'm ready to answer, or even if you come down to school and we can explain anything you want. Thank you again for listening, and see you next time. My name is Ahmed and I teach you physics.